All right, let's come together. I would like you to, in the next 30 seconds, be ready to discuss the results of your folder. If you have a question, I would like to get a question then. If you know a key idea, I'd like you to share a key idea. If you have an important detail to share, I'd like you to share that. I'll give you 30 seconds in your group to get ready. Go ahead.
Were we just talking about the 90 degrees because since there's just a y component and that's just keynote that we will mention.
No, there's no x component in this one, there's just a y component.
Yeah, because it has a straight 90 degrees.
And they mentioned that. And that's pretty much it. For the unit vector notation, we'd only have to we'd write 0 for the x component and then 15 meters for the y component.
Yeah, because we're already in magnitude.
And there wasn't much work to show for that, so yeah.
So I feel like that's all we did.
All right, let's come together. Okay, in your group over here, who's the A person? Okay, go ahead and give us something, Kevin.
After looking at all these problems that were already in the folder, we noticed that we all use the same sort of algebraic formulas to find distance. We rearranged the formula for average velocity, which is v average equals delta x over delta t, by multiplying delta t to both sides and getting delta x alone. And once we found it for both legs, we added them together to find the total distance traveled.
Total distance or displacement?
Distance,
Okay.
because the displacement would be the difference from the initial point and the last point, not the distance, the actual distance traveled.
All right. So in your group, I'd like you to just quickly summarize what he just said there and come up with your response. Go ahead.
And then you multiply the change of time to both sides, so then it's the change of x is equal to v times the change of time, which means delta x is equal to velocity times the time that was displaced during that certain period. That the displacement is from the initial point to the ending point. Yeah.
What's the difference?
Oh, because he found the mirrors separate, right?
Yeah.
So he just added to find the total distance.
Yeah.
All right,
So
yeah,
what about
makes sense.
That's all he did. And then he said like there's a difference between distance and displacement. Displacement, he said it's from the initial point to the end point.
Basically bring origin.
All right, let's come back together. Before we move on to the lesson for today, does anybody have a question about the review folder? Any questions now that you want to ask? Any questions? Go ahead.
I just want to make sure that for ours, we have to, it gives us an angle of theta and then the r magnitude.
Yes.
So we have to make a triangle on a plane. And our angle theta was 90 degrees, so I just wanted to make sure that, would that mean there was no x component?
What do you think?
Well, I know that for 45, when you have like an angle of 45, you start from the x-axis and then move up 45. So when you start, when it gives you 90, would you just move up all the way and have no x component?
Let's see. Here's a 45-degree angle. So you're going to have an x component and a y component because you're going to move to the right and then up to get to that point that has the 45-degree angle. Is that right?
Yeah.
But your question is, what if the angle is not 45? What if it's 90 degrees? Now what do you do? Now what do you do? Do you move to the right? So the question is, will there be any x component?
Yes.
What is the x component here?
0.
All right, it's important. That's a good question. In your group right now, I would like the C person in each group to kind of summarize what we just said. What did we just say?
So if there's a, if you assume a 90 degree, if the angle is 90 degrees, it's going straight up, right? So there's no components in the y direction, I mean in the x direction. So yeah, there would be no components. The components in the x direction would be pretty much it.
All right, take a moment to make a note for yourself on the conclusion there. If there's a 90-degree angle, then there's no x component because you're not moving in the horizontal direction. That's important. That's important. Take a moment to make a note in your conclusion about that. Okay, as you wrap that up, I want to bring your attention to today's topic. Today's topic is temperature. Temperature. The first thing I want you to do in your group, the very first thing. Notice the first thing on your sheet is, what do I already know? We've already had an introductory lecture on this. In your group right now, I'd like you to spend just 30 seconds to a minute discussing what you already know about temperature. So in 30 seconds or a minute, I'm going to ask you to share, what do you know about temperature? So spend that time right now. What do you know about temperature?
But the average kinetic energy of a particle. No, it's the total Fahrenheit is equal to 9 Fahrenheit.
Total Celsius.
Total
Temperature of
Celsius.
Celsius.
Plus
Plus
32. Yes. And
Plus Kelvin, Fahrenheit, and what else?
Celsius.
yesterday, right?
Okay,
So, yeah. that
let's
could be-
come back together. In your group over there, Christian, who's the B person? Go ahead.
Well, we concluded that temperature is just a measurement of the amount of heat in an object, and heat is basically just the amount of energy that it has.
Any response to that?
It's the amount of kinetic energy the molecules have.
Tell me more.
That the atoms, the molecules are made up of atoms, and the atoms move inside the molecules, and that is what temperature is.
Tell me more.
That the more movement of the molecules, the higher the temperature, and the lower the movement, the lower the temperature.
The lower the movement, the lower the temperature.
And
The slower the atoms move.
the atoms will never stop moving. It'll just it'll decrease, but it can never stop moving.
What will decrease?
The like
Kinetic
the
energy.
the kinetic movement in the
movement of the atoms, right?
in the atoms.
The kinetic movement of the atoms. All right. I like this idea. Here's what I'd like you to do right now. Write down just briefly 1 or 2 sentences what you already know. What you already know or what you think you already know. Just write it down briefly. Doesn't have to be long. Maybe 1 or 2 sentences. 1 or 2 sentences. You can if you want. Equations are fine. All right. As you wrap it up in the next 10 to 20 seconds, finish writing what you're writing. Now here's what I'd like you to do. This part of the lesson is going to be observation. That means I want you to look at the demonstration. You can get out of your seats. At this time, I don't want you writing. I'm going to give you plenty of time to write about it, but first I want you to see it. I want you to come up here in a position where you can see the demonstration, so you can get out of your seat if you need to. And I have 2 beakers. I have 1 beaker right here with a thermometer in it that reads 80 degrees Celsius. And I have another beaker right here with a thermometer in it that reads 21 degrees Celsius. So just to be clear, I have one that reads 80 degrees C and one that reads 21 degrees C. So I'll call this T sub H, and I'll call this T sub C. Of course, T sub H stands for the hot, and T sub C stands for the cold. Both of these are water, and I would like you to observe what happens. I have some red dye. I'm going to drop it in there, and I want you to observe what's going to happen. I'm going to tell you what I'm not going to do. I'm not going to stir it. So just watch for a moment. As you're watching it, you can turn to the people in your group and just make observations. You can say anything you want. Just watch what happens.
way faster.
Yeah.
Hold on. Some sort of that one order drops the street. Oh, you know what? I get it. Because the atoms are moving so much, it's kind of stirring itself. It's like
What do you mean by stirring
it's
itself?
not stirring itself, but the atoms they're moving so much that it spreads it faster than this one.
All right. All right. What do you notice happening here? What do you notice happening here? Go ahead.
The dye dispersed faster in the hotter water than it did in the cooler.
Okay. So what?
So that's just the difference. The difference is that the hotter the molecules get, the faster that they move around in the beaker. So if you put
Which molecules?
the water molecules.
Can you see any molecules in
Well,
there?
no, but you understand that because when you put the dye in, it shows how they're moving around the beaker.
What's he talking about, Melanie?
He's talking about that when you put another substance in another liquid substance in a water, that's the atoms are moving faster. So in this case, when it's hotter, that they're going to diffuse faster because the atoms are moving faster than the atoms that are in the cold.
Can you see any atoms in there?
No.
Then why are you so sure that atoms are going on?
Because of atomic theory.
Tell me more.
Atomic theory says that everything's made up of matter and atoms in it.
Okay, I want to be kind of clear. That's correct. Here we're actually talking about molecules. Which molecules in particular? Water, hydrogen and oxygen atoms that come together to make water molecules. And we can't see those. We can't see them at all. If I look in there, it looks like liquid to me. If I try to see particles, I simply can't see them. But the dye helps us to infer something. And it's helping provide evidence for the model, the atomic model that you're talking about. And I would like you to take a moment right now to sit down in your groups and discuss what kind of evidence did this observation give you about the atomic model or the molecular model and temperature. So sit down for a moment and give that a discussion.
The way I thought, like you could picture it, like just imagine there's like a bunch of tiny little balls in the water. And since when it's hotter, they're moving a lot faster. So imagine just dropping something into all that, you see the balls just moving the other liquids that were dropped in there around faster than this one. Here they just fall and they can just move throughout and they won't diffuse. They won't diffuse as fast as temperature.
Okay guys, let me be clear. This is a talking time, not a writing time. I'm going to ask you to write in a moment, but first I want you to talk. So the question is, in your group, I want you to discuss. If you look really closely at this beaker, and you look really closely at this beaker, I'm going to propose that there's an observable difference between the two. You're talking about molecular theory, atomic theory, and you're saying things that make sense in some ways, but I also want to be really clear. If you were a really bright 10-year-old, you might say, I don't see any atoms in there. And yet we have evidence. What evidence do we have? What evidence do we have to support your theory? So in your group, discuss that right now.
Alright, so using what we know of atomic theory, we know that all matter is composed of atoms. Okay? And using what we know about temperature, when the temperature increases, the kinetic energy increases. Therefore, the atoms, they shake more rapidly. They move. They keep moving. So, combining what we know of atomic theory and temperature, we know that if you disperse another liquid in there, it will move just as fast. It will disperse faster than if in the warmer water than it would in the colder water.
All right, let's come back together. In your group, Rogelio, who's the A person? Okay, go ahead.
So we can't see the atoms, right? But we just infer that they are there because the atomic theory,
Tell me your evidence.
We don't really have evidence, but we just assume,
You have no evidence?
Well, yeah, because the molecules of the dye disperse faster because of the water molecules.
How do you propose that's happening?
Because molecules always move.
Okay, molecules are always moving. Are they moving here?
Yes.
Are they moving here?
Yes.
Do they look the same? Why not?
Because there's more kinetic energy in the hotter tub or the hotter beaker.
What did he just say? In your group, who's the C person? Go.
He was saying that like the particles are moving faster in the water that's heated, so it's spreading around more.
What's spreading around more?
The molecules.
Which molecules?
The one from the dye, right?
Well, all right. I like the ideas. I want to think about this a little bit more. Look up at the key vocabulary that I've given you. Temperature, kinetic energy, heat, thermal equilibrium, and atomic theory. We will use some, perhaps, maybe all, maybe not all of those words to try to come to an idea of what's going on here. So I'm going to give you another 30 seconds in your group to kind of discuss it. The ideas that I'm hearing are sounding good, but I'd like to kind of fine-tune them a little. Fine-tune them a little. So in your groups, discuss it a little more. We'll come back.
So like the temperature is like the average kinetic energy, right? So like the hot one has more kinetic energy. Therefore, like it diffuses faster. And the cold one has less kinetic energy. So it diffuses slower than the hot one.
Maybe heat is equal to each other from a certain perspective.
All right. What do we notice? What do we notice in your group right here, Victor? Who's the C person? Go ahead, Serena.
Well, the atomic theory states that all atoms are moving and everything is made of atoms. And in this case, the atoms in the warmer water are just moving quicker than those in the cooler water, which means that the dye will be dispersed quickly, more quicker than in the cooler water. So that's why we were able to see the color faster than in the cooler water.
Responses or questions?
The atoms in the warmer water are moving faster. And they have more kinetic energy than the slower ones. So they're bouncing around more, causing the dye to disperse a lot quicker.
Is that the same thing that Serena said?
Yeah.
There's more kinetic energy in the one that's heated up more, so we could conclude that heat makes kinetic energy increase.
Okay, so the higher kinetic energy is in the higher temperature, and the lower kinetic energy is in the lower temperature. That's an important observation to make. And the evidence that we're using is we're not directly observing the molecular motion. We're actually observing an effect of the molecular motion. And so a person could say, well, you never saw any molecules in there, which is true. But what we saw was an effect of molecules moving around, and based on our model, we're kind of inferring what happened. We're using evidence to infer what happened, something that we couldn't see. I want you to take some moments right now. I'm going to give you about 2 minutes. I want you to, under your notes, I want you to write down some notes. This is a writing time now. You can draw some diagrams. So give yourselves a couple of minutes to kind of write down notes, draw diagrams about what happened. Draw diagrams about what happened.
Both.
All right, let's take a break for a moment from your diagrams. Let's take a look here. Let me give you an idea of what I want you to kind of think about. What we concluded was that higher temperature molecules are moving faster. Higher temperature molecules have more kinetic energy. What I would like you to do is kind of look at your statements and then make notes to yourself on the side. Note to self, kinetic energy is 1/2 mv squared. That's why faster moving means more kinetic energy. All right? And I also want you to be able to make more generalizations than what I've put up here. You may discuss these, but what I would like right now is that you have several generalizations that you can put under your notes. Several generalizations now based on your observations. Do that right now, please.
Before and after.
All right, I'm going to wrap it up for today, and here's how I'd like to wrap it up. I'd like you to make one generalized statement about temperature. So far, we've done some observation, we've done some thinking, we've done some discussing. I've written some kind of generalized ideas on the board. Higher temperature molecules have faster velocity on average. Slower temperature molecules, or lower temperature have lower velocity on average. Now what I would like you to do is, in your group, try to come up with what do you think is one or two sentences that can summarize what temperature measures. What does temperature measure? In your group, just try to come up with that real quick.
In anything.
Matter, substance.
In matter. It increases. It measures the movement, kinetic energy of molecules in a object, fluid, etc.
Yeah, I think that's
ETC period.
All right, let's come back together. Go ahead, Robert.
I have a question actually.
Go ahead.
Because I forget who it was, but someone had said that heat increases kinetic energy. Is that true, or is it that kinetic energy increases heat?
Well, that's a good question. So you're asking what's cause and what's effect, I think. Well, what I want to focus today is not on heat, but on temperature. Now, you know that I heated up this water because you see a heat plate right here. And so when I added energy to the system, so that's a good question, and that's something that we're going to cover tomorrow. But heat is actually energy. And when I add energy to this system, what happens to the energy of the particles? They increase because heat is energy, and adding the energy to the particles made their energy increase. But what measure showed that? The temperature. And so what is temperature a measure of?
Energy. It's kinetic energy.
It's a measure of the kinetic energy of the particles. So in your group, I'd like the B person to tell everybody what I just said. Hold on. Temperature is a measure of the average kinetic energy of the particles in that system. The B person, tell everybody what I just said.
Average kinetic energy of the particles that are moving.
the average kinetic energy of the average kinetic.
All right. Okay. Final thing before we close out for the period. I want you to make a note. What's temperature? In your own words, just write down what is temperature. What is temperature? Tomorrow we're going to finish the back of this work. And we're going to talk about heat and temperature tomorrow. But for today, are there any last questions before you go? Last questions.
Since the molecules are moving faster, does that mean that they're covering more area and they're cooling the dye with it?
What do you think?
Yeah.
Do you have evidence for that?
Yeah, that the dye is displacing faster.
That's exactly right. Okay, I'll see you guys tomorrow. Thank you very much. Thank you very much.